This is the third videotape in the IPC series on surface mount solder joint evaluation. In this video, we're going to look at two types of chip components: bottom-only terminations on rectangular chip components and cylindrical surface mount, or MELF components. Let's start with the rectangular chip components that have a single termination on the bottom side. As we discussed in the previous video, rectangular chip components have metallized terminations that vary from one component to the next. Some components have terminations that wrap around all 5 sides, and some wrap around on only 3 sides. Both of these styles are very common and are available in a variety of sizes. There is also a less common variety that has just one metallized termination on each end of the bottom surface. The problem with these bottom-only chip components is that you can't easily see the solder joint, since it's underneath the component. If you tilt the board in an angle under a viewing magnifier, you can sometimes see the edge of the joint, that is, if another component isn't blocking your view. For visual inspection, this is not a very satisfactory arrangement, but it does work. There are components like this functioning properly in many different products. The one thing that you can usually see are the physical dimensions, like any misalignment with the lands or the height of the solder joint between the land and the termination. There is also another style of chip component with terminations on both the bottom and also the end surfaces. The solder joint configuration for this two-face chip component is very similar to the bottom-only style, with the obvious difference that the double-face terminations will have a visible fillet on the outside edge. The acceptance criteria for this visible end fillet were explained in the previous video in this series on rectangular chip components. The requirements for bottom-only terminations are covered in Table 9-7 of the ANSI J Standard 001. You'll remember from the previous video that there are 3 classes of acceptance criteria, based on the application of the end product. Class 3 is for high-performance products, such as life support systems. Class 2 is for dedicated service electronic products, where uninterrupted service is desirable but not critical. And Class 1 is for general electronic products, such as consumer applications. This doesn't necessarily mean that if your company builds a consumer product, that your acceptance criteria are limited to Class 1. Your company may decide that Class 2 requirements are more appropriate for a particular assembly, or perhaps all of your assemblies. This decision needs to be made by each and every company, based on cost and reliability decisions. It's important that you know what classification your electronic assemblies must conform to and apply only those specific requirements. The first dimensional requirement we'll be discussing for bottom-only components is the minimum end joint width of the solder joint. For both Class 1 and 2 assemblies, the solder fillet must extend at least half the width of the termination, which is 50% of dimension W, or half the width of the land, which is 50% of dimension P, whichever is the smaller measurement. This means that Class 1 and 2 components could hang over the edge of the land up to 50% of their width, as long as the solder fillet covers the land and termination along their entire length of contact. For Class 3 assemblies, the solder fillet must extend 75% of the width of the termination, or 75% of the width of the land. This means that only 1/4 of the component would be allowed to hang over the side of the land, provided that the solder fillet covers the entire length of the termination on top of the land. A dimensional restriction for bottom-only components is the maximum end overhang specification. This defines how much the component termination is allowed to extend over the end of the land in the lengthwise direction. End overhang is not permitted in any class of assembly for this type of component, because the likelihood of a severely decreased soldering area is high. All other parameters for bottom-only terminations are listed as unspecified for all 3 classes of assemblies, with the exception of minimum solder thickness, or dimension G, which calls for a properly wetted fillet, and a minimum thickness of 0.2 millimeters for Class 3 assemblies. This concludes the minimum dimensional requirements for bottom-only chip components. As always, ask your trainer if your company defines other dimensional criteria not covered in the J standard for this or any other component type. Now let's look at the cylindrical end cap termination, or tubular-shaped chip components. These components have a number of different names, ranging from metal electrode face tubular shape micro-miniature leadless components to the less descriptive but slightly easier to remember, MELF, which usually stands for metal electrode face components. These cylindrical components were one of the earliest styles of chip components. The composition of MELF components is similar to rectangular chip components. The body of the component is made out of a non-conductive material, typically ceramic for resistors, capacitors, and inductors, and clear glass for diodes. This means that if the body of a MELF component touches a conductor trace, it won't cause a short circuit or any electrical malfunction. MELF resistors will usually be color-coded to indicate the resistance value of the component, just like a leaded resistor. MELF capacitors are generally color-coded, although they can be solid-colored. Most of these types of components have wraparound terminations, which give the components more surface area to solder onto. There are also MELF components that have plated terminations only on the end surfaces, and another style called the dog bone termination. Both of these are less commonly seen, but are used in certain types of products. MELF components are sometimes mounted on specially designed lands, especially if they're going to be reflow soldered to the board. These special lands will typically have a cutout or notch that faces the opposite land. These notch lands actually cradle the terminations to help center the component more directly onto the land during the reflow soldering process. As the solder paste is heated, the solder begins to flow up the component and outward toward the edges of the lands. The surface tension on the sides of the termination should help the component to center itself on the lands, as it is balanced between the two equal forces of the solder flowing both upwards and outwards. MELF components can also be wave soldered without any special land design considerations. Regardless of how the component is attached to the board, there are three basic things to look for in any solder joint. The first is good wetting of the surface. In our earlier videos in this series, we explained how the contact angle indicates the success of the bond between the component and the land. This bond is determined by the amount of attraction between the metals during the soldering process. For example, if we were to place a drop of water on a piece of waxed paper, the water would bead up into a ball. There is no attraction between these two substances. Now, if you put a drop of water on a piece of paper, you would see it flow into the surface. Solder will also flow onto a properly prepared surface. Good wetting of the solder is indicated by a low contact or wetting angle. And as we've said before, the lower the angle, the better the wetting. The solder fillet should also have a concave shape or inward curve. The higher the contact angle, the less attraction there was between the two metals. Although there are exceptions, a contact angle in excess of 90 degrees usually indicates poor wetting and is not acceptable. Non-wetting is a failure of the metals to be coated by the molten solder, so that the original metal surfaces are partially or completely visible. This is often caused by contamination or insufficient flux. On wave soldered assemblies, there may be an occasional joint that never comes into contact with the molten solder because of the shadow effect. This effect on a particular joint is caused by shielding of the area by the component or other adjacent components. Complete non-wetting is an unacceptable condition for any class of product. De-wetting is the withdrawal of solder after initial wetting. De-wetting is characterized by irregular droplets of solder, often with a thin film of solder between them. De-wetting is usually caused by contamination of the surfaces and is considered an unacceptable defect for any class of product. The second thing we need to look for in a solder joint is the quality of the fillet. Ideally, the fillet should be smooth and free of holes. On some solder joints, you may occasionally see a slight dimple caused by shrinkage of the solder as it cools. Shrinkage dimples are only cosmetic imperfections. They should not be confused with voids or blowholes. Voids and blowholes are caused by gas or flux that becomes entrapped in the solder. As there are no criteria defined for these types of imperfections in the J standard, your company will have to define its own position for these types of defects and also decide when they become process indicators. The appearance of the fillet also depends on the composition of solder and the type of material being soldered. There are several different types of solder based on the percentage of tin and lead they contain. Connections made from different alloys may not look alike, but all of the joints on a particular assembly should be the same general color and texture, provided they were produced by the same process. If there are one or two discolored joints on an assembly, these may be caused by some type of contamination. The third thing to look for is the correct amount of solder. It is possible to have too much solder, which can make it impossible to see if the metals are properly wetted. You can also have insufficient solder, which can result in a mechanically weak connection. We'll be discussing the maximum and minimum amounts of solder in the next section of this tape. But let's stop now and make sure that you understand everything we've covered so far in this section. Next, let's look at the physical dimensions for MELF component solder joints. The reason we're concerned about the amount of solder in each joint is almost always for the same reason: solder joint reliability. To understand this concept, we need to examine the effects of heating and cooling on the solder connection. The most severe heating and cooling cycle occurs during the original soldering operation. Both the board and the components are subjected to temperatures as high as 260 degrees C for a short period of time. The different materials in the assembly will expand at different rates whenever they're heated. Now let's consider a particular solder joint in a consumer product like a TV set. Every time the television is turned on, heat builds up in both the components and the board. The ceramic components won't expand as much as the base material. This means that the circuit board will be pulling on the solder joints whenever the assembly is heated. When the television is turned off, the board will shrink back to its original state. After years of heating and cooling cycles, something begins to happen to the structure of the solder.
Oh, God!
You've probably noticed how you can bend a piece of wire several times before it finally breaks. The internal structure of the metal is becoming damaged as it is stressed by bending. After the metal is sufficiently strained, it will eventually crack and break. This is known as metal fatigue. A similar type of failure can also happen to a solder joint. That's why we want to have an optimum amount of metal in the connection. In general, the less metal you have in a solder joint, the less the joint will be able to absorb the strain of expansion and contraction. Each solder joint should have a sufficient amount of solder to absorb this movement over the lifetime of the product. Now that we understand the importance of having enough solder in every connection, let's look at the minimum solder joint sizes for MELF components. These dimensions are called out in Table 9-6 of the ANSI J Standard 001. The first dimensional requirement is the maximum side overhang, or Dimension A. Dimension A is measured from the furthest edge of the component to the closest edge of the land. Why are we concerned with this particular measurement? Sufficient solder, as we just explained, is probably the major reason. But we also want to avoid reducing the gap between adjacent components or between the component and an adjacent conductor. If an overhang condition reduces either of these gaps below the minimum electrical clearance called out in your company's specification, the joint will need to be reworked. The J standard allows only 25% of the component width to hang over the edge of the land, for all three classes of assemblies. Again, this is from the furthest edge of the component to the closest edge of the land. You might remember from the previous video, Class 1 and 2 rectangular components are allowed to hang over the land up to 50%, or half of their width. The reason that MELF components are not allowed to overhang as much as rectangular chip components is that the bonding area and solder volume of a circular solder joint decreases rapidly as the overhang increases. The strength of a rectangular connection is reduced by the overhang in a less critical manner, simply due to the physical shape of the solder joints. Another requirement has to do with the amount of overhang allowed from the end of the termination to the edge of the land, or dimension B. None of the three classes allow any amount of end overhang, and this is true for all surface-mounted chip components. MELF terminations for all three classes are also required to have some degree of end overlap. That is, the terminations must extend onto and over the land. The next dimension we're concerned with is the width of the solder fillet, which we'll call dimension C. Dimension C is measured at the thinnest part of the solder connection. The minimum in-joint width required for Class 2 and 3 assemblies is half of the thickness of the component, or 50% of dimension W. There is no in-joint width specified for Class 1 assemblies. Just as long as there is a good solder fillet that meets all of the rest of the dimensional criteria, the connection would be acceptable. The next requirement specifies dimension D, the minimum side joint length of the solder fillet along the side of the termination. Class 2 requires a solder fillet that extends at least half the length of the termination, or dimension T. Class 3 requires at least 75% or 3/4 the width of dimension T. Class 1 requirements specify only a properly wetted fillet. The final requirement is the minimum fillet height on the end and side of the MELF termination, or dimension F. Class 3 requires the solder fillet to extend at least 25%, or 1/4 of the height of the termination, plus dimension G, minimum solder thickness. There is also a minimum solder fillet height of 1.0 millimeters. As long as the fillet meets the smaller of these two requirements for Class 3 assemblies, the solder joint would be acceptable. Both Class 2 and Class 1 require only a properly wetted fillet of any height to be acceptable. As with rectangular components, the solder may not extend up onto the body of the component as a maximum fillet height limitation. That concludes the dimensional requirements for the placement and soldering of MELF components. And while it would be difficult to remember every requirement for all three classes of assemblies, you should be able to remember the specific requirements for the class of assemblies your company produces. And you can always refer to the ANSI J Standard 001 to verify these dimensions. It should almost go without saying that no one expects you to measure every single component to see if they meet their dimensional criteria. Most solder joints will look perfectly normal. It's only the unusual ones that will require special consideration. And remember, you're always looking for these basic attributes: good wetting and a solder contact angle of less than 90 degrees. No evidence of non-wetting or de-wetting. The general smoothness of the joint, including the absence of voids or blowholes, and the correct volume of solder, not too much and not too little. In most cases of excess solder, you should still be able to make out the shape of the end termination. Now's the time to discuss with your trainer the important points covered in this section of the videotape. Part 4 in this series will continue with gull wing solder joint evaluation using the ANSI J standard 001.